Last video, we talked about capping output tokens. You set a hard ceiling on how much the model can write back. That's layer one done. Now we move one level deeper. Here's the question I want you to sit with. When you send a message to an AI chatbot, what exactly gets sent to the API? Is it just your latest message? Or is it everything? Every single turn of the conversation, all the way back to the very first message you typed? The answer is it depends entirely on how the developer built it. And that one design decision can be the difference between a chatbot that costs you $10 a day and one that costs you $500. Today, we fix that. I'm going to show you a technique called the sliding window. It's simple, it's powerful, and it's the first real weapon in layer 2, input control. LLMs have no memory. You provide everything. Before we can fix the problem, you need to understand something fundamental about how LLMs work in an API context. These models are stateless. Every single API call starts with a blank slate. The model has no idea who you are, what you asked 10 minutes ago, or what it replied. Zero memory. So if you want it to feel like a continuous conversation, if you want it to remember context, you have to send that context yourself on every call. This is the standard pattern for building chatbots. You maintain a list, usually called the messages array, and you append every new turn. Then you send the full list every time. Token growth is cumulative, and it compounds. Look at this table. On turn 1, you might send 200 input tokens. The system prompt, your first message. By turn 10, you've accumulated 2,000 input tokens per call. By turn 50 in a long session, you could be sending 10,000 input tokens every single time the user presses enter. And remember from video 3, you pay for every input token every call. The model doesn't get a discount because it already read that message last time. It reads everything fresh, and you pay fresh every single call. Cost example. Model Claude Haiku 3.5. Input price 80 cents per 1 million tokens. Session 50 turns. Average 200 tokens added per turn. Input tokens sent per call grows 200 to 10,000. Total input tokens across session nearly 255,000. Cost for one session input only nearly $20. At 1,000 daily users, nearly $204 a day from input tokens alone. $200 a day just from one layer, and we haven't even counted output tokens. At scale, this is the number that kills AI products, and the fix is surprisingly elegant. So what is solution for token growth? The idea is simple. Instead of keeping the full conversation history, you keep only the last n message pairs. When a new message comes in, you slide the window forward, dropping the oldest messages and including only the most recent ones. Let's see how sliding window history is working next scene. On screen, messages 1 to 10 visible. New message arrives. Message 1 drops off left. Messages 2 to 10 remain. Message 11 enters right. Window slides. Think of it like a conveyor belt. The window is a fixed length, say the last 6 exchanges. New messages step onto the belt from the right. Old ones fall off the left. What you send to the API at any moment is only what's currently on that belt. This completely stops the token growth problem. Your input cost becomes predictable and flat. The question you'll immediately ask is, how many messages should the window hold? And the honest answer is, it depends on your use case. Let me give you a framework. Window size 2 to 4 exchanges, best for short context tasks, one-off Q&A, factual lookups. Window size 6 to 10 exchanges, best for general chatbots, customer support assistance. Window size 12 to 20 exchanges, best for technical help desks, code assistance. Window size 20 plus exchanges, best for specialized agents with long reasoning chains. For most of you building your first AI product, start with six. That's six full exchanges, six user messages, and six assistant replies. You can always tune it later based on what your users actually need. Now, it is time for implementing what we discussed in Python code. But before code part, we'll clarify very important and common trick in lossing critical information. This is a very important concept when building LLM applications. Every request sent to the model contains three main parts: the system prompt, the conversation messages, and optionally other context such as RAG documents or tools. The key point is that the conversation history uses a sliding window. As the chat becomes longer, older messages may be removed to stay within the model's context limit. However, the system prompt is always sent with every request and is never dropped. That's why critical information, such as instructions, rules, persona, or user preferences, should be placed in the system prompt rather than relying on old conversation messages. In short, conversational context can be forgotten, but system-level instructions persist throughout the entire interaction. This example shows the difference between storing important information in chat messages versus the system prompt. On the left, critical details like the user's name, skill level, and preferences are stored in the conversation history and may be lost when older messages fall outside the sliding window. On the right, the same information is placed in the system prompt, so it is included in every request and remains available even after hundreds of conversation turns. User questions belong in the conversation history, but long-term instructions and preferences belong in the system prompt. This section explains why the system prompt is so important. It provides consistency, reliability, and better user experience because critical instructions are always available to the model. A simple analogy is to think of the system prompt as a policy manual that is read before every task, while conversation messages are like daily notes that may eventually be archived. The key takeaway is simple: put permanent information in the system prompt and keep temporary conversation details in the message history. System prompt equals permanent rules, messages equals temporary conversation context. Hello, this is a code part. In this lab, we'll show what effect of sliding window for context conversation in reducing token cost. Firstly, after installing the unit libraries and loading the Claude API, we start our code with showing the history conversation, okay? Without applying any window size by the first defined function called shareNav. These functions first define user messages about user is a request or query. Then this query is going to the model. Here, the model name is Claude. Then the output is append again to the conversation history. So firstly, we define conversation history as blank list, then start to append the user message query. Then, after getting the feedback from the model, we append the model response. Then I make three calls for our functions. Okay, share name with the user message. If want to see printed output and see the result. Firstly, I make three call for the function, so I make what we call three turn. First turn is number of input token is 17 and number of output tokens. For this, answer of the models about the Python. And then number 2, call for the functions, turn 2. Input tokens here is 338 and is for output tokens. But look at the input tokens. The input tokens now is a cumulative between the output tokens plus the input one, plus some other token numbers. Okay, but the input token accumulative for what the message last feedback message plus user query. And if we go to turn 3, we find also the input token more increased. This is coming from the last two term feedback plus user query. Now I start to apply what we say is sliding window approach. What it means, sliding window? Sliding window means I define the win size. For example, here define 2, and 2 here means 2 exchange, means 2 turn, and 1 turn take 2 message, one for user query and one for model. So here I define one size, 2, that equivalent to 4 message. Same code, just start with the user message, append on 4, append the 4 to the conversation history empty list. Then apply window size. This window size means the conversation history will take around 4 message. Okay? Then what I mean 4 message is 1U and 1A. 1U is one user, and 1 here is the answer from the models. So if you were talking about 4 message, so I will talk about 1U, 1A, till 4U, 4A. Till here, we're talking about 4 other message. Okay? Then I append the response of the model, okay, to the conversation history. And let's see what the output I make for 1, 1, 2, 3, 4, 5, 6, 6 equals. Okay, for this function, and let's see this output. But take care here, for there are some tricky here. What is it? I will tell him, my name is Fatih, and then I live in Riyadh. Then I like football. Okay? Then I love Egypt. This is how many message? 1, 2, 3, 4. And the number 5, I ask, returning to ask him about my name. So due to the window size here is for 2. That means for message, so the model memory stop at 4 message. And from 5 message, now he dropped the first one. So 1, 2, 3, 4, it's okay. All this stored according to defined one size. But from 5, number 5, he dropped now the first message. So expect when I call and send the model this message, what is my name? He says, I don't know. You didn't mention my name. Why? Because the window size here dropped the first message from the middle history. Let's see what's the output. First turn. This is the answer of first turn. Okay, I told him my name is Fathy. So he answered when I told him my name is Fathy, he answered here, nice to meet you, Fathy. How can I help you? Okay. Then the second one, when I told him I live in Riyadh, he says, Riyadh is the capital of Saudi Arabia and the vibrant city. Then, number 3, I told him, okay, what's number 3? I like football. What he says answer, this is wonderful. Football is a popular sport in Saudi Arabia and around the world. Number 3, yes, number 3 here. Okay. Number 4, I told him I love Egypt. Okay? So what he says in turn number 4, he says, that's great. Egypt is a fascinating country with a rich history and culture. Start from number 5. When I send him and I told him and asked him something, what is the name? What is my name? Okay. Due to window size, he dropped this message. So he didn't know my name now because he's dropped this message. We see his answer. When I tell him, what's your name? He says, I don't have any information about your name. You haven't told me your name in our conversation. See? So this is a window concept exactly. Window is meaning as you going in conversation with someone. The old is dropped according to the configure window size. Now let's see the cost comparison, okay? For naive model, that means you don't apply window. And for window context applied. If we make this comparison, for example, 20 turn, okay? 1, 2, 3, 4 till 20. And in each one, I will print the naive token and the window token. You can see and the naive cost and the window cost. Firstly, we can see we start with 200 token, okay? Next turn is double, 400. Third one is multiply by 3. Fourth one is multiply by 4. Multiply is the beginning, okay? Last, number 5 is multiply by 5. Then start from number 6. You find now we're going to 1,200. But try to observe from number 7 what happened to the tokens. now became 1,400, but now is 100,420 or 200 only. And they continue like this till end of the turn. Why? Because you reach here to the window token size. So, is just here, you make a window size, okay, to be window 6. So, start from number 7. He start here in window size, start from number 7. He didn't increase about increase 1,200, okay? And they continue like this. If we calculate the native cost, and the Windows cost, okay? And they make a graph for native token and the Windows token, and the windowed window token and the native cost and the window cost. You see? Start from turn number 7 that exceeds the way configured window size. The native, the sliding window continue as fixed horizontal to 1,200 only. No increasing. But for the native, native means no window light. He increasing linearly and gradually. Okay? And if you here calculate the cost, we find this orange one is the cost for applying slide window, and the blue one without applying the slide window. We can see there are big difference between the cost of the native and between window token. So here, if we talk about production, for production cases, okay, how we can set the model context, we will set as fixed or dynamic. Actually, this answer this question. Usually, we make our context window based on dynamic, based on the maximum input token that we set this parameter. So for every time of conversation, you see here every type of conversation, he is example. First thing user sends, then this is the reply on the model. Okay? For 1, 2, 3, 4, 5, 6, 7, 8. And every time I make estimation of the token. Okay? First time is 4, second time is 6, 4, 10, 6. Then a submission of this reach 128. And in this example, I make maximum input token to be 880. Okay? 80. And then that means he starts from last message. Okay? Last message he sent. How many token is 40? So start to subtract from the maximum every message token from the last. So here, the maximum is 80. The result is 40. The remaining, okay? Number 7, message number 7. What is left is 3 tokens. So 40 minus 3, 37. The number 6 is 50, 55. If we subtract 37 minus 55, 5 token, the result will be negative. That means no, I can't. Now I exceed the maximum input token. In this case, I can't take this window size. So my window size only will be around, include the 7 and 8 message, and the old one is dropped on us. And old one from 1 to 6 is dropped message. Okay? See here, the fixed window, 3, 4, 5, 6, exceeds the token limit because longer message. But for token aware, I only added parameter. And if the token during conversation exceed, now I stop. So here, the last 2 only was kept, but the old one are removed. Let's bring this together. Every LLM API call you make is stateless. The model remembers nothing. So if you want conversational context, you send it yourself. And if you send everything, every time, your input token costs grow without limit. The sliding window is the first and most direct fix. You store the full history locally, but you only send the last n exchanges to the API. Input costs go from a compounding ramp to a flat line. 3 lines of Python. But here's the limitation we haven't solved. What happens when someone asks, wait, didn't we talk about X a while ago, and X is outside the window? The sliding window literally cannot answer that. It has forgotten. So what do you do when you need to reduce input costs and maintain access to older context? The answer is the next strategy. Instead of dropping old messages, you summarize them. You compress the old history into a short paragraph and include that in the window instead. Same savings, but nothing truly lost. That's episode 7, and it's one of the most satisfying techniques in this whole series. See you in next episode.